Okay, Bernard, thank you. So this is the basic makeup of what we refer to as a linear power supply, right? We've been talking about this, and each one of them's got its own functions. Of course, what we've added on most power supplies is we'll have a unit right here that we refer to as a transformer. In fact, that's what it is, right? And what's the transformer doing for us? Yeah, but it's actually what's eventually going to determine what we get on the output, right? You understand that? Then we have the rectifiers. What does the rectifiers do? Yeah, converts AC to pulsating DC. And then what does the filters do? And then what does the regulators do? Yeah, but it converts unregulated DC over to regulator DC, right? And of course, that means exactly what Brian says. It means it tries to maintain a constant output, even though this input is changing. So this input is going to vary also, right? Who provides that? Alabama Power. Here it's going to be TVA. And it's all over the place. So I can measure my voltage here, and you can measure your voltage at your house, and they are not going to be the same, right? Understand? Then also with changing loads. So changing loads, we're talking about current loads, right? You understand? So if the load requires more current, the tendency of a power supply is to drop its voltage down, right? You understand that? And then if you unload it, it's a tendency to go up, and that's what the regulator is trying to do for us. It's trying to maintain. So when you do load it, it goes down, right? You understand? And you can actually see an unregulated power supply. Of course, that will be any battery. Don't do this on your car because it's got a lot of amps, but you can measure the output voltage on like a AAA battery and put a resistor across it, and as soon as you do it, the output voltage is going to drop down because of the internal resistance of the battery itself, right? You understand that? And when it's unloaded, so a 1.5 volt battery, which most of our C and D cells are supposed to be 1.5 volts, that's when it's outputting its current, right? You understand? So when you measure it unloaded, what do you think your meter is going to show you? Well, it needs to show you about 1.6 volts. Y'all understand that? So you can check batteries without loading them. So if you got one that checks 1.4 volts unloaded, what do you need to do? You need to get rid of it because when you load it, it's going to actually drop down below that. So this is what regulators do, and we're going to regulate. We'll first start regulating with a special purpose diode called a Zener diode, and then we'll look at some actually regulators. Usually they're 3-terminal devices, and we'll look at some of those. These are actually integrated circuits. And what is an integrated circuit? You've probably heard it before. So we got a circuit, and you built circuits in DC, right? And what do they consist of? Well, in DC they consist of a lot of resistors. But what happens is what we do on an integrated circuit, we take the entire circuit. So used to you could look inside a stereo and you'd see hundreds of transistors, and you see this, but stereos have been around so long. Now you open up a car stereo, you're going to see one big old IC because all the circuits have been what? Integrated onto a single piece of wafer. And that's what a regulator does. So a regulator will have an unregulated input. It might be 1 pin. No, an IC can be a regulator. So a regulator is a circuit. If I can take that circuit and put it on one single piece of silicon, so instead of having all this stuff over here, so instead of come over here, having a reference, having this guy right here, this is a pretty cheap regulator, coming over here and taking this and going up to this device right there, coming out here, right? You understand? What we can do is we can take all this and put it on a what? Put it on an integrated circuit. And then instead of me having these transistors and these Zeners and these current sensors, so we have sensors out here that actually tells us when we're going to overcurrent the thing. So we come over here and so instead of doing that, we come over here and take that whole circuit right there and put it on a piece of wafer. So over here, what we have is we have unregulated in, we have common. We always have to have a common. And then we have a regulated out. Well, how many things do I need? Well, all I need is 3. So I can put these things in what we call a 3-lead device or a 3-terminal device. So one of the leads that come out of the bottom, this is where I put my unregulated in. One of them would be what? Regulated out, and the other one would be what? Would be the common to my circuit. And now instead of the problem with what advantage does this have over this? Well, if that device goes out, I can fix that. If that device goes out inside this, then I'm replacing the whole thing. So what we're talking about, integration makes it easier for us to troubleshoot because now we're troubleshooting one component instead of 10, right? You understand that? But the problem is it would be a lot cheaper to fix that. This would be more expensive to install, but it would be cheaper to fix. This right here would be cheaper to install, but we don't fix these things anymore. What do? We just replace them. So this would cost a lot less than the individual components. If you did all these components and added them together, it would cost more than that right there. So of course, more and more manufacturers are going to this. Why? Because it's cheaper to install, right? You understand? So it's cheaper to manufacture. And back in AC, you're going to learn that the DC average of an alternation is 6.73 volts peak, right? You understand that? Times Z peak, right? I mean, this right here, if you took 2 and divided it by pi, you'd come up with 0.637. So that's where that number actually comes from. So this is, to me, is the easiest way. Instead of remembering 0.637, is to remember this V peak over pi. But y'all got that on your formula sheet somewhere, right? 2 V peak over pi. So we was looking at a half-wave rectifier. So what do we mean by half-wave rectifier? Well, this is an AC waveform. So it consists of a positive alternation. It consists of a negative alternation. When we talk, and these should be identical to each other, guys. Mine's it. Well, what we mean by half wave is we just use one of those. We either just use the negative alternation or we use the positive alternation. We strip the other one off. So that means if I could bring this in, insert up. I need to go in and on this computer and get rid of all this stuff. I just had no time. So it means if I come over here and use this device right here, let me change to a black. And that's a symbol for a watt. Yeah. And what does a diode do? In one direction, right? So I'm going to come over here and I'm going to point this back toward my AC signal. And then we'll come over here and of course we'll put this on a load. So instead of me doing that, let me draw the symbol for an AC signal. So the symbol for an AC source is nothing but a circle, and then it's got the sine wave symbol inside, and that's the symbol for an AC source. And this is a symbol for a true common, which means it's isolated from ground. And of course, this is supposed to be the symbol that we use for ground, right? Okay. You see, sometimes you'll run into that, and this is why I try to color that in. So which alternation is it going to let through? Well, we know to forward bias it, we have to make this guy here positive in respect to this guy. So we've got this connected directly to the source. We've got the cathode pointing to the other side. So when this side right here is positive on AC, this side right here would be negative. So the cathode is pointing toward the negative. It don't mean it's going to be negative, but it's pointing toward the negative, right? So this side is still going to be positive, but it's going to be less positive. Then this is going to allow current to flow from here. This is going to be the negative side of the resistor. This is going to be the positive side of the resistor. It flows back to the source. So what's going to happen is this guy right here is going to, if I was looking across the resistor, it would give me that right there. Everybody okay? Yes or no? Now, when the power supply, when the AC input changes directions, then this is going to be negative. This is going to be a positive. So here, the anode is pointing toward the negative. The cathode is pointing toward the positive, right? You understand? So it's going to cut off. It's going to act like an open switch, which means I get zero current through my load. My load drops no voltage. Now, if we were to look across the diode, what we'd see across the diode is we'd see exactly the opposite. So here it drops all the voltage when it's off, right? You understand? And in this, it drops almost no voltage when it's on. It is not a closed switch. It acts like a closed switch when it's forward biased. And if it's silicone, it's going to drop about what? Yeah, about 0.7 volts or 0.700 millivolts. And then, of course, when it's forward bias, it's going to drop the entire thing, right? You understand? Because the current flow through it is very, 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 very small, and our meter won't be able to get that. And what do we call the flow that flows through it in the opposite direction? It's called leakage current. And what controls the leakage current? We've already talked about that too. It's controlled by one thing, of course, the voltage across it that it's trying to block. So it's actually two things. Forward biased. So forward biased it acts like a closed switch. And then what we call reverse bias, it acts like an open switch, yeah. So right now, if I was to go over there and look at these light switches right now, and I was to measure across the switches, what would we measure? God, I hope not. That's what people think, though. Okay, so to get voltage drop, V is equal to I times R. How much R does a switch have? None. Okay, so V is equal to 1,000 amps times 0. What does our answer come up and get? 0. So right now, and that's what the diode does, it drops no voltage when it's forward bias. I mean, if it was a closed switch. So yeah, I go and measure across these light switches right now. They're all going to measure 0. If it measures 2 or 3 volts, I'm going to pull that sucker out and throw it away, because a closed switch, guys, has an ohms that we don't even understand. It's so low. So every meter I've got right now in this shop would go over there. I'd measure 0 volts across that switch, right? You understand? Okay. Now what happens if I open the switch? Now the resistance goes up to infinity, which means basically it's going to measure the applied voltage. Why? Because nothing else in the circuit is dropping it, and people don't. I don't know how to teach this, and I wish y'all could let me know. So I've got 5 resistors right here, or just 3, and I come over here and put a switch right there. So y'all tell me how I need to teach this, because people have problems with this, and I don't know how to teach it, I don't guess. So here's my voltage source. How much voltage would that resistor right there drop? None. How much voltage would this drop? None. How much would that drop? None. So that's basically, if this drops no voltage, that's basically taking that minus right there and putting it on the other side of that switch, because nothing in there is dropping any voltage, right? You understand? And the positive is sitting right there, so that's why you measure the applied voltage across an open in a series loop, right? You understand? Because nothing in the circuit is dropping any voltage. So if I went over there and turned the light switch off, we figured out which one, I'd go over there and measure 100, what we call 120 volts. Odds are it's not going to be 120 volts. It's just that the National Electrical Code calls that the optimal voltage. So in NEC, that's what they specify all the time, 120 volts. Your power company specifies 120 volts plus or minus 10% is what it guarantees it can give you. So that means when this thing is open, it's going to draw across the diode. It would drop the negative alternation because the resistor is not dropping anything, because it's acting like an open switch. When it's forward bias, if it was a closed switch, it would drop 0 volts. But it's not. It's not a closed switch. It's a diode, right? To understand, and it's always going to drop a voltage. And we have to take that into consideration. So that means if I've got 6.3 volts, of course, when we talk about AC, if we don't specify, we're going to assume it is RMS, right? You understand that? And it stands for root. It means root of the means of the square, right? You understand? Most people abbreviate and call it root mean square. So what would the peak voltage be if it's 6.3 volts RMS? Don't know. I'd have to do a little math. No, we're over on this side. We're not over here. So I know what you was thinking. Go ahead. So look at your formula sheet. Find VRMS on there. Should be one of the first formulas at the top, because this is the first basic formula we said. It was what? So we're trying to calculate V peak. This is a nice sine wave, so we got this 0.707 we can use. Okay. Is V peak going to be greater or less than RMS? It's going to be greater in its name, because it says what? Peak. And I try to tell people, well, the peak of a mountain. So I've got this magic fraction, 0.707. And if I multiply by a fraction, I come up with less than what I started with. If I divide by a fraction, I come up and end up with more. So what I'm going to do is I'm going to take VRMS, which is 6.3, and I'm going to divide it by 0.707, and that will give me VP. Now, why do you need to know this? Well, what advantage does an oscilloscope have over a meter? You actually can see what's there, right? You understand? What advantage does a meter have over a oscilloscope? Well, the meter is showing you the work you get, right? You understand? The oscilloscope is showing you what's there. So the problem is that I come over here and I measure 6.3 volts on my meter, and I come over here on my scope and I measure 30 volts peak to peak. Then something in my head goes, well, that's got to be wrong, right? You understand? So we have to go from this to peak. My scope measures peak to peak. So what's 6.3 divided by 0.707? What's that? 8.9. So that means I missed it. It's 18. I said 18 volts, almost 18 volts peak to peak is what my scope would measure. Okay, so 8.9 volts peak, which would be 19.8 volts peak to peak. Y'all understand that? Yes or no? Peak to peak. Okay, so, yep, thank you. I can't do math. Thanks for checking them. 17.8 volts peak to peak. And why is that? Gives you half. Yeah. Okay, that makes sense. Everybody okay? So what would we have over here? Maybe. We would actually have 8.2. Because of your diode. It's forward biased, it's going to drop 0.7 of a volt, right? So 8.2. So what would my DC meter measure that's going to show me how much work I'm going to get? Are we going to get 8.2 volts of work? Why? Are we getting 8.2 volts of work out? I said no, but why? Well, how much work am I getting right here? None. Yeah, so what we're doing is we're taking this 8.2 and somehow we're averaging it with 0, right? You understand that? Okay. So the average of a DC wave is this guy right here, 2V peak over 2V. Most people say 2V peak over pi. This person has put the V peak over to the side. So that means here we have 2V peak over pi. It's averaged with what? 0. Then here I have 2V peak over pi again, and then we average it with what? A 0. So basically we just drop the 2. So the average we get out over here would be, so my DC average, DC, would equal to approximately 8.2 divided by pi. And what are we going to use for pi? We won't even use the pi key on our calculator. We're just going to use 3.14. That's a good point. Should be on the second row of formulas, if I remember right. First page. The bottom don't get until we get into transistors. DC average half wave right here, formula 14, D peak over pi. D peak over pi. D peak out. So what I'm doing is we're going to, oops. We're going to refer to this as D peak secondary. And we're going to call this right here D peak out. Yeah, so we'll D peak secondary. Because normally what would our actual AC source be? Our actual AC source is going to be a transformer. Because Alabama Power and TV Base is trying to give me 120 volts. And I put 6.3 there, so we need some device that takes AC and converts it to a lower voltage, right? So here we have maybe 2300 volts over here. And then over here on your house, you have a step-down transformer, and we call it a center tap transformer. And what we have across the two outsides, you have 200, center tap transformer. And you can see why, because what that means is they take the secondary and they put a conductor right in the center of those lines. And we refer to this as a center tap transformer. And how many of these are there out there? Millions, yeah. Because every house, well, every group, very few people that they use a center tap transformer for one house. So usually you got 4 or 5 houses on one transformer, right? And this is where we get it. So what would happen is that it steps it down. This is center tapped. And that means if I go from here to here, we would get 240 volts AC. And from here to here, it would give us what? 120. And that's what's nice about a center tap transformer. So what they're giving us on this one is they're calling this guy 0 volt, but that's not exactly right. The trainer shouldn't do that. So what we have is we have 6.3 volts here, which gives us what? 6.3 volts there, which would give us what right here? 12.6 volts there. Am I going to measure 12.6 volts? No, right? For one thing, the transformer's unloaded. And another thing, that's if I had it watt over here on my primary, if I had exactly 120 volts over there. So it's probably going to measure more because it's unloaded. But that's okay. For our calculations, we'll just use what the transformer's rated at. And then we'll understand our calculations are going to be perfect, but our components are not. Right? You understand that? So I'm going to go across the 6.3 volt transformer, one of the 6.3s. here's a 6.3. I'm going to hook this to what they're calling 0 volts, but if I wanted 12.8, I would go over there. This is totally isolated, guys. So I don't know why they did that. They called this 0, but that would be if I go between here and here, right? You understand that? Then I'm going to come over here and take this. It could be any color, by the way. And what do we want? Do we want a negative supply or do we want a positive supply? And what I'm going to do is I'm going to take my node, which is the side that don't have the stripe, and I'm going to point it back towards the source. So that's the way you can identify whether it's a positive supply or a negative supply. All you do is see what section of the diode is pointing back towards the source. If the cathode points towards the source, then it's going to be a positive supply. If the cathode points towards the source, it'll be a negative supply. The red wire is, well, no, this is the source, but there's a resistor between this. We're talking about the lead of the diode that's going to connect directly to the source. I could use any color here, but this AC has no polarity. These are just the colors that I grab, right? I could use black on both sides. Why is this pointing toward this? So between this and the source, we have a resistor. This, though, this is the guy that's pointing directly to the source. Okay, so if I had a meter, what should we expect? So we take V peak, which we've already calculated, right? So we calculated V peak. Oh, sorry. So we calculated V peak to be 8.2, and we're going to use V peak over 5. So my DC is going, my volts DC, and this is what we're going to measure, would be equal to 8.2 divided by 3.14. So my meter should measure around what? 2.6 volts. And that's how much work we're going to get out of this. That's exactly how much work we're going to get. And this is DC. But it's going to be pulsating. So we'll look at this with an oscilloscope too. See how good Joe did. So I'm a meter on DC, right? And this is an auto ranging meter. And I'm going to come over here and I got to plug my trainer in. This is a trainer we're going to fix. That on it. And I'm going to come over here and turn it on. Put your meter across here, Rich. And across the low, because that's where we want it to be, right? 2.4 volts. We calculate 2.6, right? And 2.4, we missed about 200 millivolts. Just using the ratings, right? You understand that? So this is how much work we're actually getting. Now, this is actually fluctuating. This is what's nice about this meter. It's got an analog scale on it. Most meters, you can't see what's actually going on. This one we can actually see that this DC is actually pulsing. Can I see that? If we look at this one, Now we're isolated from ground. So this on the oscilloscope is grounded. So the oscilloscope is grounded. So that means as soon as I come over here to this, I've established a true earth ground. So that means you cannot put a nut. So I cannot use the scope directly to measure stuff inside the circuit. I can't put another ground in here. I don't understand that. Okay. Let's see what this actually looks like. First of all, when you turn your scope on, it considers the center to be your 0 volt reference. That means we're measuring AC. So over here across the diode, so we don't have auto range scopes. So we're going to turn the volts per division. What I want to do is I want to put more volts per division. So it don't work. What we're trying to do is keep the top. So what we're trying to do is possible, make it as big as we can make it, and not the top. Volts per division, and then I'm gonna set it in the center. What I'm gonna do is I'm gonna since we're gonna try to measure this, is I'm gonna put the bottom line. Then I'm gonna move this to the center. Okay, so 5 volts per division. So okay, the division. So display brightness. Okay, now it's right. 5 volts per division. 5, 10, 15, right? Everybody understand? If I'm counting in one, let's see, 15.24 volts. 15.4 volts. Is that right? Yes, sir. See that? Okay. Okay. Let me try to get it. Huh? Yeah, I'm sorry. So for division, let's see, we're 2 divisions, right? So everybody understand? 5 volts per division. So each one of these must be 1. I'm sorry. So these would be 1. So that would be, he said 17 volts. 5, 10. Now you can do it this way too. If you count in ones, then how much would each one of these be worth? If there's 5 divisions, if you're counting in ones, so I've got this would be 0. This would be 1, right? And I've got 5, so that'd be worth a 0.2, right? You understand? Which is what I was doing. So I could come over and count them 1, 2, 3.24, 3.4, and then I can multiply that times 5. So that's my volts per division. So whichever way you see it. Most people can count in 5s, most of you count in 2s, right? You understand that? So if I'm counting in 5s, then each one of these would be worth 1. So it'd be 5, 10, 15, 16, a little over 17 volts. And scopes are not extremely accurate, but they're accurate enough, right? And my time, I have it on 5 milliseconds per division. So what I do to measure time is I try to line up. What you need to do is stretch it out as you can and still do one cycle. Okay. And then what we do is we use move it over. And I can count this. This is 5 milliseconds per division, so we'll probably have to use a scope, a calculator. 1, 2, 3, 4, 5, 6.2, 4, 6. Multiply that by 2.5. What answer are you expecting? Yeah, I know it's hard focusing. So wait, I want 2.5 milliseconds per division. So all I'm doing here, can y'all see what I did? Yes or no? So we got two controls. This is our volts per division. I'm looking at channel 1, volts per division. Notice when I change this, the yellow one is changing down there. Okay. Is this guy right here? It's called horizontal position. And then what I'm trying to do is I'm trying to adjust the horizontal position so I can line up a spot here on the vertical line. And then if I line it up, then this would be 0, right? 1, 2, 3, 4, 5, 6. And each one of these, since I'm counting ones, each one of these would be 0.2, 6, 0.2, 0.4, 0.6, 6.6, right? Times 5 milliseconds. And what do y'all come up and get? Hopefully you come up to be real close to 16.7 milliseconds. So this is Alabama Power. So your scope is going to measure two things. It's going to measure voltage peak to peak. And it's going to measure voltage peak to peak. And it's also going to measure time. Now what I'm going to do now is I'm going to move my scope over to the other side of the diode. So this is actually across the load. So here's my scope. I'm moving across the load. Right there. Of course, I can see the diode. It would probably be better. It's a firmer lead. And then what we do is now we have halfway. Now I'm measuring DC. So when we measure DC, what we can do is we can put this. I usually put my 0 reference down 1 above the bottom, and that way we can get more accurate, right? And then what's going on now? Yeah, the trigger, right? Now I can add more volts per division, and this is still the best we can do right there, guys. So that right there is DC. It's not AC, it's DC. Okay? Yes, no? Center. Turn on channel 2. It's the same thing. It's the wrong thing. Sorry. Yeah, 0 volts on top of each other. What I want you to see is that you can't see it there, but what I'm going to see is that the yellow one is slightly lower than the blue. And why is that? Exactly right. 17. Well, look, it's basically a mirror image So we cut off this guy. Notice we have none on the top. We cut off the bottom. We only let the tops come through. And then this is why we have to take out that 7/10, because we lose that watt when we're forward bias. We lose that diode drop. Now what we convert this over to negative power supply. Flip the diode. I'm going to turn off channel 2 again, and we can see now we have a negative supply. But it's going to measure about 2.6 volts, and now it's going to be negative, right? You understand that? And all we're doing to determine if it's a negative power supply or a positive power supply is we look at the diode. The diode is going to be pointed direct. It's going to be connected directly to the source. Here the cathode is pointing directly to the source, so this is a negative power supply. So that's all you have to do, guys. You don't have to figure out forward and reverse bias. Just look at the diode, right? You understand. And if the anode points directly to the source, then it's a positive power supply. If the cathode points toward the source, it's a negative power supply. And you don't have to worry about, okay, it's forward bias, reverse bias, because you couldn't see it anyway. Because it's forward bias one half cycle, and it's reverse bias the other. Huh? Okay. And this is half wave. What does half wave have? Well, normally we have a transformer, and then we have one diode. It's very, very cheap. But we're getting half of it, which means, number one, it's not going to handle as much current as a full wave, right? Understand? And the voltage is not going to be as much. So full wave, we're going to find out we're going to get twice as much. Half wave, then we get half wave. Do y'all understand so far? Very, very. So this is where we start off with power supply, right? You understand? First thing we do is once we get it to the level we want with our transformer, transformer, then what we're going to do after that is figure out full wave or half wave. This does not require, this guy here does, number one, it does not require a center tap transformer. So I don't have to have a center tap transformer. I can just have a regular transformer. And hopefully, a center tap transformer is going to cost more than an untapped transformer. The one that we've got is, and I'll show y'all the one that's on the trainer. It's got at least one center tap, and it's got multiple. This guy turns off. So what should I expect out? Y'all need to work this. If I use the whole transformer, 12.6 volts, what should I expect out?